Hey guys, so I was going to try something a little different with this tutorial. I know the last one I did, I actually typed it out while you guys were watching, and the last time I did that I actually got some stark criticism. So I'm going to try it this way. So this code actually puts a sprite to the screen and it bounces it back and forth. So as you can see right here, sprite going side to side. So mostly what I'm going to focus on right here is how we load up the image, how we set up our shaders, how we pass the information to the shaders, and how we draw it. So let's go through the code. So this is all, I'm going to skip over the boilerplate. I'm going to go right to the main parts, which is first we load up the image. Now this is pretty straightforward. If we go into this code, it's populating a buffer with the RGB A data. Now in my last one I was using a BMP, so we didn't have any alpha channel data. I'm using a unique pointer. I'm using the move semantic. So the idea is we can generate the array here dynamically, and because we pass ownership to the caller, it becomes the caller's responsibility to clean it up, but because we're using the move semantic and unique pointers, that's guaranteed. This is more code quality, so really this code is not very interesting. It's pretty straightforward, loading up the buffer and passing it back to the main code. So now I'm going to skip ahead and we're going to go to the compile shader code. Now the shaders are the actual programs that are executed in the GPU cores. And we can have numerous shaders. So right now this guy is only loading a single program. So if we go to the shader code, we see we have a vertex shader. And the vertex shader is run once per vertex. So if we were drawing a triangle, this code would be run 3 times. Now the fragment shader is going to be run for every pixel that makes up that triangle. So there's going to be a lot more fragment shaders depending on, like, if this is a filled in triangle, the tessellator will actually figure out where all the pixels, and it'll feed that information to the fragment shader. Now these are pretty straightforward. I'm not going to go into details to these yet. I'm going to wait till we get to the buffer information. So very quickly, just to go over, since the graphics card is the one that's actually going to be compiling and storing this information, and the OpenGL is pretty much based on state machine. You call create shader, you tell it what kind of shader you're making, and it'll allocate the memory and it'll return you a resource number or resource reference. Same thing with the fragment shader. Then we tell it to we tell it to compile the shader. We get the shader source, so that's this guy right here. So we take that string, we push it into the graphics card, we tell it to compile. Now part of the reason we compile this at runtime is based on the graphics card you have, it might not be the same instruction set as another graphics card. So all the graphics cards actually have their own GLSL compilers. So we compile it, so I believe that's where we get the information back. So we've compiled it, we get the status back. If it failed, then we didn't get our compile thing executes. Now debugging shader code is nightmarish. Last time I looked, they didn't really have good debug tools. So if it crashes, it'll give you an error code, but if it's like not doing exactly what we want it to do, I've seen people actually write shaders where it would put a pixel to the screen to show that the levels of execution. So if it was red, it got this far. If it was green, it got this far. That's kind of a testament to how big of a pain in the ass they are to work with, but also how powerful they are. So exact same thing, we compile the fragment shader. Same thing, comes up here, grabs the code, compiles it, and then because now we've actually bound the graphics card knows which ones it has on hand. We could say create program. I'm sorry, we haven't bound it yet. We can say create a program, and you can think of the program in this case more like a pipeline. So this is a collection of shaders that go into the pipeline. So you got your vertex shader, you got your fragment shader, you got your geometry shader. So that's going to constitute an entire program. So we say, hey, graphics card, allocate me a resource for my shaders. It says, okay, here you go, and its number shall be nya, and then you could attach the shaders to the program, link it, and boom, Bob's your uncle. And pretty much if you got it past compile, it's going to link, so we don't even have to worry about checking for it. So that returns us an integer value that represents a reference to our compiled shader pipeline. So pretty straightforward. That's pretty much boilerplate. Now, why this is bad in this level is we may have multiple shaders for different types. So right now I'm just doing a very simple sprite to screen, so the shader's very simple. I think it'll become apparent when we go through the buffer code why it's very simple, but we can also do a lot of really cool things with it the way I've got it set up. So the compile shader, we are probably, when we're done, we're probably going to, like, I've started a very simple resource management thing here. In fact, we call our active entity thingy. We're probably going to have the buffer, we're going to have the program number, we're going to have all sorts of references to how these resources are stored on the graphics card. So take away all the different entities. They might share a shader, they might have their own shader. We're going to have to work that into our resource management. Alright, so okay, now we're going to go back up here to the bind buffer. So remember, when we read the PNG, we've actually have an array that represents RGBA pixels that was grabbed from the PNG. Probably don't want to do it this way with the width and the height. We probably want to return an entire element excuse me, for this guy. So, you know, all we have to do is say, hey, give me this PNG as an entity, but for right now, the width and the height are actually very important to keep track of. Not only does it tell us how big this guy is. Now, if we stored it as something like a vector, then we could get its size, but there's a reason I chose to do it this way. Lower overhead. So, moving forward. So, as I said, the graphics card wants to keep track of all these resources. So, we're going to go into our bind function. And I know I've got it around here. GL functions. Alright, so when it first comes in here, it converts the RGB pixels to float RGB, and that's kind of a misnomer, I need to change it. It does more than just do the RGB. It also encodes the position information into this buffer. So I'm going to open Paint here for this because I kind of think it would be useful to have a helper. So right now we're getting RGBA, RGBA, so on and so forth. So each one of these values represents an unsigned character. When we are passing it through this function, you notice we're going through the rows on the outside and the columns on the inside, the Y and the X. Now, and we're building a brand new buffer right here, so the destination buffer. So when this function runs, what it's going to do is it's going to be X position, Y position, RGBA, X position, Y position, RGBA for every single pixel. So let's see, RGB, yeah, 4, 5, 6. So as you can see, we got 6 GL floats per pixel in this array. That is very important to keep track of. Again, we're probably going to rewrite how this works. I'm just doing a general overview. So Now we've got our updated buffer. Now it has its X and Y information in there. So just like the shader programs, we tell the graphics card, hey, I'm going to generate a buffer, or arrays. They call them vertex arrays here. So, and we can say, like, we just got to give it a pointer to put it all. So right now we're only getting one, so I just have it, you know, at the address of this guy. But we could say, hey, I'm about to generate about 20 arrays, and you give it a array to be populated. It'll give you all of your reference numeric values. Okay, so this part is just saying I'm going to work with this vertex array. So if we got 20, we would have to do this for each. We would have to do this operation for each and every buffer. So since we only have one, we say, hey, I'm working on this one. Card is a state machine. I think the example I gave recently is if the graphics card is like a storage area. You know, we're allocated so many units, and each one of those units is numerically referenced. So I'm saying I want to work with this storage space. I might be killing it, so I'm going to stop and move forward. So we get our buffer. This is, of course, our destination buffer with our X and Y and color data combined into one. All right, so we generate, let's see, an actual buffer that will be bound to this storage ID. We tell it what kind of buffer we're making. And then we actually push the data into the buffer. So actually, okay, my bad. The array is a collection of buffers. Sorry. So we generate our buffer. We say it's going to be an array buffer. I know this is a little ambiguous, and I apologize. We're pushing in our buffer data, and we're getting it from the position in RGB data, and it's going to be static draw. Now this is going to become a little more relevant later. Okay, now here's the important part. This is where we set up our layouts. So right now we're going to be setting up attributes for our buffers because, and this is going to become very important later, the layout tells the shader, or tells the graphics card, how this data is relevant to the shader and how to pass it in. So you notice here we're saying layout 0, its size is 2, the values are floats, I have no idea what this means, and the stride is 6. So what does this mean? So if we come back to here, what we're saying is our first bit of data that needs to be isolated from the rest, and okay, it's right here, is these first two floats. So 2 floats, and we start at the first element. So that's what that last guy is saying right there, is that we're starting at buffer 0, offset 0. So this is going to isolate this portion as layout 0. Alright, so the next one is the array attribute array 1, and that gives us, so I think we can have like up to 16 attributes. I don't know that off the top of my head, but so we can pretty much set these up for every buffer, and we could have it all laid out differently if we wanted to. We could pass it information to the shader that's only relevant to the shader for doing something cool, like an explosion per se. But okay, moving forward, sorry, I'm getting off topic. So the next one says, okay, for layout 1, the size is 4, so we're going to have 4 GL floats. It's not normal. It's not normalized. Still don't know what that means. The stride is the size of the float times 6, and you notice we start at GL float offset 2. So that's saying this is where this layout starts, and it goes 4 elements, so it chops it off. Oops, right there. So picture that looking, actually that kind of screws up my thing there. So picture it Picture these X's and Y's and RGBAs being separated. So the stride actually says to get to the next layout 0 element, we go 6. So if we go over 6 GL floats, we start at the next one, so on and so forth. From this particular, we start at the RGBA. Again, we go over 6. We wind up at the next one. So pretty much all this is doing is this is interleaving the data in the same place, and we're telling it how to process it. Then we bind the buffer. Actually, what we're doing here is we're cleaning it out. So once we've got all this set up, when we say GL bind buffer to 0, that means that clears out the state of the graphics card. So since we've only got this one thing we're working with, this is good. All right, so now we've got our shader and we've got our buffer and our buffer information stored on the graphics card. So now we come into the fun part. This is the main loop. Excuse me. Actually, I'm going to back up just a little bit. This is matrix math, and this, we as developers, we're not going to have to worry about this too much. This is pretty much boilerplate. This is actually giving setting the coordinate system. So I believe that's left side of the screen is -75, right side is 75, bottom is -75, top is 75, and the Z is -1 to 1 because we're only working with a 2D plane. Now, this is actually 3D. We're just drawing everything on a plane. This is the viewport, and if we wanted to scroll, this is what we would mess with. The perspective is what gives everything perspective. All right, so coming down. All right, so our main loop, pretty much while the window is open, and I've skipped over all the window generation stuff. That's pretty boilerplate. We're not going to have to worry about it too much. GLFW actually provides us with our keyboard, and I believe it even handles joystick stuff pretty simply. All right, so we clear out the screen. I cleaned it out with that blue color. This actually applies it. Check for errors. All right, now this is important right here. The model matrix. This is what is applied to the. Excuse me. This is what's going to be applied. So when we move our character around, in fact, when our character was moving side to side like that, that's handled by this right here. As you can see, I started out at 0, so it's at the origin for that particular object. And I pretty much just decrement it by 1 times direction, and if 1 exceeds 51, then it multiplies direction times -1, and that's what causes it to go back in the other direction. So this we're going to get into later. Probably how this is germane right now is if you're thinking about how we're going to store these entities, they're probably all going to need their own matrix that represents their rotation, their scale, and their translate. So just FYI. All right, now we're getting to the part where I am going to show the relationship between the shaders and the buffer arrays. So notice right here we're multiplying these matrices together to make MVP. Just log that away in your mind. So we bind the buffer by its buffer ID. So this is actually going to open up our unit that has our buffer in it. And this is going to load the GL shader program that we built earlier. So now the graphics card is loaded with these two. These are just some attributes that are loaded to some of the other shaders. I think this goes to the tessellation shader. Could be wrong, but all this does is it blows the pixel size up for us. Alright, now this is important. So GL uniform matrix, pretty much what we're doing here is we're setting a variable that is going to be global to all the shaders in this program, or this, this pipeline. Alright, so that's pretty much all that's doing is that's loading our MVP math into this guy, into here. Sorry. So this variable will be passed over to the graphics card to be given to the shader. And this is the guy that actually goes and gets the buffer and starts the pipeline on it. And you can see we're passing it as GL points. And so, what does that do? All right, so we already know that, okay, we already know that this mess has been loaded into the buffer. This is the information that's going to get passed to our shaders. So if we actually go look at our shaders, the first thing that's going to be run is the vertex shader, and that's going to be run once per vertex. So notice we have layout 0, which we set up as our x and our y value, so that's being loaded into a two element vector, that is our position. And we've got our RGBA values. It's going to be coming across as a vector 4, vertex color, layout 1. So that's what we were doing earlier, is we were telling it how to read this. Now, like I said, this is going to be run for every single vertex we have. So for all intents and purposes, this is vertex 1, this is vertex 2, and so on and so forth to end vertexes. So each one is going to get one of these units. So if you can see right here, we take the x and y information, we multiply it by our matrix math that we passed in through the uniform. So this is the same, the MVP is exactly the same across all the shaders. So just for fun, let's say that image was 50 by 50, so we got 2,500 shaders running this, each with their own x and y, but they all get this one global. So each x and y for the final position of this shader is multiplied by MVP. Since we're not using z, that one's set to 0. So if we wanted to actually work in 3 dimensions, we would have to expand this to take a z. So we'd have to put a z into that data, but we're not there yet. And this is actually, that has to be one that has to do with the matrix math. So we're not going to get into it. Now, so the vertex shader has now determined the GL position. Now, this is what I was talking about earlier with how much fun we could have if we wanted to. Like, let's say we wanted to have our character exploding into pieces. We could pass a 2D vector that is the position of the origin of the blast, and we could modify this equation so that the final value would be, you know, opposite direction. We could also pass it time, so we could have a nice little explosion set up. We can do a lot with this. In fact, I'll send a link to the GL shader stuff, and the amount of stuff you can do with the shader is pretty mind-blowing. Anyway, so GL position is going to be, that's a variable provided by OpenGL. That's where this vertex will finally be positioned. And this will, you notice that we loaded this as out. So vert color out. So this value is going to be passed to the fragment shader. So all we're doing here is we're passing the colors straight through because the colors have absolutely no bearing on the position. Again, we could have fun with it. We could have, based on the position, have the color modified. Like if we wanted to do something with light sources, we could have the color, you know, get a yellow tint based on its distance given here from something. So I'm saying there's a lot of power in this stuff. Sorry. Okay, so fragment shader, very straightforward. We're getting our invert color, which is coming from right here, which is just these RGBA values passed from this guy. So because of the way we're doing this, this won't always be the case. We've got a one-to-one relationship between the vertex shader and the fragment shader. And, you know, like I said, if we were drawing triangles, this one would run 3. This would run for every pixel that makes up the triangle. So We're getting in our vert color, and all we're doing is we're passing it out to the pipeline. So that's it. That's how the shaders work. We've given it our buffer data. We told it how to interpret the data. And this is why debugging it is such a nightmare. If you have like a glitch in your array, you can't debug these values to see where they're going. Anyway, moving forward, because I wanted to keep this short, but I'm at 25 minutes. So that's it. That has drawn to the next screen buffer. I hate that we use the word buffer so much, but I apologize. But excuse me. So now we've drawn our character to the screen. We check for errors. No errors. Huzzah. We release the buffers. We put the card back to its base state. We swap the buffer so we can draw the next screen. And then this stuff is just getting the time after. So this whole execution constitutes a single frame. So all this stuff that's recording time is giving us our frame rate. And I'm not going to get into that too much. I just wanted to go over what's going on with the OpenGL. So, to conclude, this is just to give you guys an overview of how this stuff kind of sort of works and give you an idea about the possibilities. I'll be honest, I just came up with that light source thing right now. I thought that's a pretty cool idea. But anyway, I'm going to post this. You guys give me your comments. Tell me if it makes sense to you. Now that you know what's involved, be thinking about like what kind of attributes a thingy is going to have. And I hope to talk to you guys soon. Bye.